Hello, and welcome to our ongoing series of webinars around simulation and some of the interesting things that you can do with it. Today's topic is simulation in cybersecurity testing, an area of increasing importance to our customers and to the industries that we serve in general. Let's talk quickly about what cybersecurity testing is. Basically, it's the process and techniques that are involved in protecting sensitive data, which is obviously something that we're all concerned about, computer systems, networks, and software applications from cyber attacks. And the why of this is actually pretty clear. The reputational and financial harm that can result in not performing cybersecurity testing throughout the life cycle is quite high and is increasingly well understood. And although a lot of the interest stems from the high profile hacks that we see in the news these days, those are largely related to data breaches. And so again, there are true reputational harms that arise from this. There is financial penalties to the companies that are hacked. And yet that's not the industry that Wind River typically serves. We work more in the embedded space. And in that space, there's a larger threat that relates to the supply chain. So the problem of integrated global supply chains, where there are a number of actors, not all of whom are well understood or well known, creates an enormous set of threat surfaces that have to be adapted to. So even though you may feel that you have good processes in place, these can always be improved to harden up the system at the end of the day. Let's talk about one of the examples of something that was hardware initiated, although it manifested itself as a problem for people who are trying to access web services. So back in 2016, the Mirai IoT botnet attack occurred. And these were consumer grade devices that had security vulnerabilities that were easily exploited, easily discovered, and related to essentially having an IP address without sufficient security. So a threat surface that was exploitable. And what ended up happening is that 500,000 devices were co-opted into this distributed denial of service attack and took down a number of well-known and high-profile internet services, so that there was a deep financial penalty. Now, there wasn't a lot of knock-on from that. Now, this was resolved. People understood how it occurred. It opened everybody's eyes to the problem of consumer-grade IoT devices potentially being hijacked. So, the important thing, though, is not to believe that this isn't a problem for perhaps more industrial applications. Despite the fact that security was clearly an afterthought to the IoT developers and the designers of the types of devices that were co-opted in that attack, it's understandable as to why. They are, low-cost devices. They have to be brought to market quickly. They're under enormous pressure to be competitive. So security can always be dealt with later. And one would imagine that couldn't possibly happen in a safety critical embedded system, because we have a long history of building to very strict standards, right? Well, that may be true. And I want to make it clear that despite the fact that I'm using this as an example, it's not a knock on any specific aircraft manufacturer. I am absolutely certain that the aircraft in question was well designed and designed to the specification of its time. However, these devices live in the world for a long time and often have to be retrofitted with new capabilities or new systems that were never envisaged in the original design. So in the case of the well-documented hack that occurred on a Boeing 757, what you had was, a bored passenger who was a security researcher and decided that, he would see whether or not he could exploit some of the bolted on Wi-Fi systems to get access to the engine management. And in fact, by going in through the entertainment system in his seat, he was able to get access to the system and did nothing, right? It was not a malicious attack. It was just, hey, is this possible? The most scary thing is that this particular researcher did not have to clear security with any specialized hardware. They simply took knowledge of a bolted-on system that had pre-existing vulnerabilities to get into a system that the designers believed was secure. And you think, well, this isn't probably a huge problem because Wi-Fi is relatively easy to test and therefore relatively easy to patch. And going forward, we should be able to resolve problems like this now that we're aware that this problem exists. But the problem, of course, is that in embedded systems, they're usually built using hardware that's quite mature. So legacy systems for which there are no testing tools present a real problem for people who are building new systems. Now, we're not going to throw away functional technology that exists and has been well used and is well certified. So a good example is CAN bus, which is often used as the Internet of Things on a particular device. It's a well-established technology. People use it. It's great, but it was designed in an era before these kinds of vulnerabilities existed. And so there aren't a lot of testing tools to make sure that these vulnerabilities don't creep into your design should you use that hardware. And in fact, there was a study and a discovered vulnerability that could be exploited by anyone who had physical access to an airplane. And they could get access to the overall system, inject false data into it, and potentially cause a loss of the airplane, or at the very least ransom the airplane and its utility to its owners or lessees. So effectively, a disgruntled employee with enough knowledge could do something like this. And that's problematic for people who are designing safety critical systems. Our families rely on these things, our economy relies on these things. These systems that we're building have to be robust, they have to be secure, and they have to be future proof in case things come along in the future that we weren't aware of when we designed them. This presents a real challenge to designers who are thinking about these problems today. And if that weren't tricky enough, then the fact that software is adding more value and increasingly adding more value to an overall solution causes another layer of headache to people who are building these secure embedded systems. So as we add more value through software, we either, knowingly or inadvertently add new cyber attack surfaces. And as they become more complex and more interconnected, predicting what those are in advance is almost impossible. There's also a business pressure that is being brought to bear that it's not new, but it's accelerating. And that's to deliver solutions at the speed of relevance to your customers. So in the past, where a consumer or a customer of yours may have been willing to wait a couple of years for a solution, now it's quite likely that they're saying, here's the deadline, meet it, or we'll find another supplier. And that causes an enormous strain on development teams. Now, although I have these last bullets listed as challenges, in fact, I think it's the opposite. I think they're opportunities. So the fact that engineering teams are now adopting agile methodologies, or they're doing continuous integration and test and delivery of software, the fact that you're doing these activities more routinely and more quickly is an opportunity to do software and cybersecurity testing early and often, as long as you have the right tools. So how do you do that? How do you validate the confidentiality, the integrity, the availability of data around which the value of your solution is built? How do you make sure that the data at rest and the data in motion is protected? How do you make sure that those pieces of data are not vulnerable to attacks and ransom? And then if you have to do penetration and adversarial assessments on embedded hardware, how do you make sure that this is non-destructive? It's expensive and difficult to acquire hardware for a reason. You don't want to burn too much of it in your testing. How do you make sure that the human system interaction is properly tested and those threat surfaces are well exercised? We know that human actors, either malicious or just inadvertently, can cause enormous damage to systems. And this has to be tested for, even in embedded and legacy systems. And then how do you do it sooner, more often, more accurately? And on top of that, because I'm recording this webinar as I'm working from home, imagine trying to do these things in an emerging threat environment if your employees are not physically in the office and are unable to access physical hardware to validate and patch potentially known vulnerabilities as they emerge. I would like to propose, since you've visited us, that Wind River Simics can form part of the toolkit that you use to solve these problems. So Wind River Simics is a full system simulator. It allows you to simulate complex systems, which is quite a mouthful, but it's actually a really simple concept. So we take physical hardware, things that you're purchasing, things that you're using to construct your system, and we turn it into a virtual platform that can run on any hardware anywhere. So your remote worker could take a virtual target and run it on their laptop or their home computer through a secure portal, right? And this virtual hardware allows you to do a number of things that you can't do in physical hardware. First, you can test and simulate and stress test just about any size of system. So I could take one simple processor, a peripheral on that processor like my CAN bus, a network of these devices, and I can begin to do things in my virtual world that I can't do in my physical world, like inject problems or record the system state and play it backwards. The other power of this is that at least in security, in the domain of security, there are a lot of different skill sets that need to be brought to bear. This is not just a simple debugging task. Oftentimes you need to bring together a number of different disciplines. The fact that in a virtual platform, my developer, my testing leads or my testers, and my security researchers, they can all be working on the same type of hardware. They don't have to fake it or potentially retarget or recompile my application to run on the hardware they have available. Everyone's using the same target hardware, which leads to great efficiencies and different ways of collaborating. Symix has a range of features. This slide describes a number of them. I'm just going to focus on a couple that matter to security research. So the first is that you can inject faults into a system and cause it to fail. And that's a really powerful capability when you're thinking about exploiting vulnerabilities. If I know about a vulnerability, I can create a test that injects that vulnerability or flaw, especially into the hardware, and see how my system responds and is hardened or not in this case, right? And that particular test can then be added into a library of tests and rerun whenever I want. The other power that Symix brings for security research specifically is the ability to share system checkpoints. So if the system fails under a particular vulnerability, and I'm not even sure why it's failing, I can actually create a system checkpoint and share that with colleagues around the globe, no matter where they are and no matter what their expertise is. They can then take my system checkpoint, restart Symix, and get right to where my failure was. And as if that wasn't powerful enough, Symix allows you to zoom in on the problem because you have full control over the system clock. So unlike physical hardware where time runs in one direction, on a virtual platform, I can run the system clock forwards and backwards until I narrow in on the exact failure mode and then do my proximate analysis or my proximate cause analysis. The other power of Symix is it doesn't just work on your machine, it works the same way on every machine. So the fact that each run is deterministic and you have full repeatability means that your teams are more efficient when they're collaborating. These are tough problems to solve. And having to wait for somebody to be able to reproduce the error on their machine can actually lead to a lot of delay. Sometimes these security problems need to be patched much more quickly, and delay is not acceptable. So we like to say that our customers use Symix to deliver better software, faster, and at lower cost. And these are all aspects that are important when we're thinking about security. You should be delivering software with as few day zero defects and vulnerability as possible. And being able to deliver it faster and being able to do it at lower cost is just going to help you be more secure. This isn't just marketing fluff. We actually have a number of customers who are using Symix to address this exact problem space. The example I'm going to use is a bit generic, but the US Army does use Symix to deal with their OT&E mandate, so they can test physical systems before they're deployed. And in the past, if they were doing things with real hardware, which was part of the mandate, they would have to set up a physical test rig, which would take potentially weeks or months in some cases to properly set up so that it was at a point where they could test a problem or a vulnerability or a series of tests. The hardware was expensive. It's physical hardware. It has to be acquired and properly put together. And if for any reason there was a failure during the test, it wasn't as though they could reset it. It was a time and money that was lost. So by switching to Symix, by taking that physical test rig and turning it into a virtual test rig, they could go from testing in months to testing in minutes. And so that acceleration, that ability to retest and test and test and test is actually the benefit that I was alluding to earlier. By doing agile development, by testing more often, the chance of a defect slipping through is lower. It sounds counterintuitive, but it's not. And so this notion of using Symix for cyber penetration testing or cyber threat assessment is a very powerful one. And we've seen good adoption in the market and actually quite high success rates in terms of people using it this way. So in summary, I hope you found this information useful. We have more information available at windriver.com, and I'll share that link with you in the next slide. But I do want to talk about or stress the importance that we see in testing early, testing often, and testing more accurately with full repeatability. These are the kinds of techniques and tools that will allow customers to build the kind of mission critical infrastructure that we all rely on. We know that in the embedded space, it's tricky to do testing because sometimes you're working with legacy devices or you've got an integrated global supply chain. So stress test your system and inject faults with CIMICs to figure out how the system responds. And then finally, in this time of isolation and working from home, that doesn't mean that you need to stop this discipline. In fact, you can embrace it and be even more efficient by using CIMIC's virtual platforms that are available to your team worldwide. So thank you very much for your time. Please visit us at windriver.com/CIMICs for more information and take a look at some of the other webinars that we've recorded on other topics such as DevOps and digital twin. Thank you very much, and I hope to see you soon.